Hello, hello. Hello? Ooh, 10-second delay. Okay. Nah, like 4 seconds. That's chill. Oh, I guess everything's already running. Oops. Okay. That's there. And that's... I keep forgetting. Oh wow, apparently Intel is in serious trouble. Hope it works out for those guys. Alright, alright. I think that's working. Okay, so while I wait for... I'm still just gonna wait a bit. I'm just gonna see if I can turn off this thing at the top. I cannot remember how to do so. Ah, shoot. I do want to turn this thing up at the top so that I can have, can I just... Oops. I don't know how to do that, honestly. What am I doing? There we go. And now it's gone. How's that worked? No, of course not. Module does not exist. Why would... Yeah, that's fair. Reasonable. Can't return something that don't exist. Still broken. Hmm. Shame. Well, looks like we're gonna have to have two separate little things. Hey, yeah, that looks nice, doesn't it? Absolute shame. Is this working now? Or is the error still there? Who knows? Hey. Confirm all I was trying to do here is to try and get rid of this little thing up here, because I want to use Tmux. If this crashes, I still want to be where we were. But honestly, I still do doubt we're going to need this terminal. No idea why I keep opening it. I haven't used it in like 3 different chapters. No, implementing an object-oriented design pattern might have something in it. We got an ownership inventory, design trade-offs maybe. Who knows? We might actually be in console today. Yep. Probably not though, but if we got anything to test, we'll still have to do that. Anyway, let's, for aesthetic purposes, keep it like that. Alright. I'm really just gonna start out. This is not a very important chapter, to be honest. It's just who's gonna do object-oriented programming when you're doing a low-level language like Rust, honestly. Unless you're working with very old systems that you're trying to convert over, right? I don't really see why you would need... Well, I mean, you could use this design pattern. It's not like it's objectively bad. It's just not something that I tend to see with things like C, C++, even some larger languages. Object-oriented programming doesn't tend to come in when you don't have a garbage collector. I am curious to see, though. Maybe I'm going to be convinced that this is the design pattern for me. Anyway, let's start out. Object-oriented programming features of Rust. Are there built-in stuff? Are there built-in stuff? That is a sentence. Is there built-in stuff? I'm quite curious to see. Like, I guess so. Features of Rust. A lot of languages like this don't have it, and we just have to go by a design, or like just by the paradigm. Object-oriented programming, OOP, is a way of modeling programs. Objects as a pragmatic concept were introduced in the programming language Simula in the 1960s. I've never heard of this. That is really interesting. I want to look that stuff up later. Those objects influence Alan Kay's programming architecture, in which objects pass messages to each other. To describe this architecture, he coined the term object-oriented programming in 1967. Many competing definitions describe what OOP is, and by some of these definitions, Rust is object-oriented, but by others, it is not. In this chapter, we'll explore certain characteristics that are commonly considered object-oriented, and how those characteristics translate to idiomatic Rust. We'll then show you how to implement an object-oriented design pattern in Rust, and discuss the trade-offs of doing so versus implementing a solution using some of Rust's strengths instead. The way that's written seems to directly state that Rust's strength is not in OOP, that Rust is not strong in the OOP department. It seems more like an imperative language to me so far, honestly. Characteristics of object-oriented languages. There is no consensus in the programming community about what features a language must have to be considered object-oriented. Rust is influenced by many programming paradigms, including OOP. For example, we explored the features that came from functional programming in Chapter 13. What is Chapter 13 again? Iterators and closures. Yep, okay. Right? Arguably, OOP languages share certain common characteristics, namely objects, encapsulation, and inheritance. Let's look at what each of these characteristics means, and whether Rust supports it. Objects contain data and behavior. The book Design Patterns, Elements of a Reusable Object-Oriented Software by Eric Gamma, Richard Helm, Ralph Johnson, and John Lycides? Addison Wesley Professional, 1994. Locally referred to as the Gang of Four book. Okay? Is a catalog of object-oriented design patterns. It defines OOP this way. Object-oriented programs are made up of objects. That's a pretty good definition so far. An object packages both data and the procedures that operate on that data. The procedures are typically called methods and operations. Using this definition, Rust is object-oriented. Structs and enums have data, and the input blocks provide methods on structs and enums. Thought we were Is it Monday? Oh shoot. No. Completely fair. I forget what day of the week it is until I get an alarm for this. Continually. Hey, you haven't really missed anything, we're just defining object orientation. Rust is object-oriented because of structs and have data. I'd argue that the terminology should here be. Oh, anyway, welcome back, Sorbet. It's good to see you. I'd really argue that it should be, the language they should be using here is supports object-oriented behavior, because you don't really need to use these things, though in something like Java, you kind of do have to be object-oriented. And same with JavaScript. Everything is an object in JavaScript. Even in literals, it's insane to look into it. Even though structs and enums with methods aren't called objects, they provide the same functionality, according to the Gang of Four's definition of objects. I'm curious to see the debate. Like, what are they going to describe? Like, in what definitions they don't support OOP? I'm quite curious to see what. I don't know. I can't really put to words what I'm thinking here. Apologies. Another aspect commonly associated with OOP is the idea of encapsulation, which means that the implementation details of an object aren't accessible to code using that object. Therefore, the only way to interact with an object is through its public API. Code using the object shouldn't be able to reach into the object's internals and change data or behavior directly. This enables the programmer to change and refactor an object's internals without needing to change the code that uses the object. We discussed how to control encapsulation in Chapter 7. We can use the pub keyword to decide which modules, types, functions, and methods in our code should be public. And by defining everything else, and by default, everything else is private. For example, we can define a struct averaged collection that has a field containing a vector of i32 values. The struct can also have a field that contains the average of the values in the vector, meaning the average doesn't have to be computed on demand whenever anyone needs it. In other words, average collection will cache the calculated averages for us. Listing 17.1 has a definition of the averaged collection structs. We have a list and an average, which is a float of F64s. A float of F64s. What am I talking about? A 64-bit float. The struct is marked pub so that other code can use it, but the fields within the struct remain private. This is important in this case because we want to ensure that whenever a value is added or removed from the list, the average is also updated. We do this by implementing add, remove, and average methods on the struct, as shown in listing 17.2. Implement average collection. We have a function add with a mutable reference to self and an i32 as a value. It simply pushes the value to the list and then runs update average. Public function remove does the opposite, just pops that piece out of the list, matches on the result, some value, if there is a value. Ah, yes, I see. Pop takes it out and then places it into the result variable. If we have a sum output, self.update average. If we don't, do nothing. Good stuff. Or I guess return none? Yes, just return none. That's always going to get me. I'll never not be confused by this, I'll admit. Just the lack of a semicolon is the return statement. That's never not going to get me. Average just returns the average. Function update average just gets here's a total, which is an i32. Self.list, get the list vector, create an iterator, and then use the sum method on the iterator to sum up all of the i32 values. Then simply self.average equals total as F64. Yeah, I guess. Divided by self.list.length as F64. Yep, we're just typecasting here to floating points, 64-bit, and dividing them. Pretty easy. This is just some basic object-oriented programming. The public methods add, remove, and average are the only way to access or modify data in an instance of average collection. When an item is added to list using the add method or removed using the remove method, the implementations of each call the private update average method that handles updating the average field as well. We leave the list and average fields private, so there's no way for external code to add or remove items to or from the list field directly. Otherwise, the average field might become out of sync when the list changes. The average method returns the value in the average field, allowing external code to read the average, but not to modify it. Because we've encapsulated the implementation details of the struct average collection, I should just say, just to go back to terminology, this is just a getter and a setter. That's all this is. Because we've encapsulated the implementation details of the struct average collection, we can easily change aspects, such as data structures, in the future. For instance, we could use a hash set I32 instead of a vec I32 for the list field. As long as the signature of the add, remove, and average public methods stay the same, code using average collection wouldn't need to change. If we made list public instead, this wouldn't necessarily be the case. Hash set of I32s and vectors of I32s have different methods for adding and removing items, so the external code would likely have to change if it were modifying lists directly. If encapsulation is a required aspect for a language to be considered object-oriented, then Rust meets that requirement. The option to use pub or not for different parts of code enables encapsulation of implemented details. Now, I could be disagreeing with some incredibly intelligent people here, but I really don't think that encapsulation is a necessary thing for a language to be able to support object-oriented behavior. I really do believe that a person should think about these paradigms as just what they are, paradigms. They're things that coders have to work with. I do support having some form of structure in place to force the paradigm, if that's what you're going for. However, I really don't like the language stating that it supports object-oriented or that it is object-oriented. Sorry, I would prefer the supports object-oriented type of language. Because again, you absolutely could do everything the exact same way with a language that does not support encapsulation or even private methods. You just gotta have programmers who understand the rules and follow them. Right. Inheritance as a type system and as code sharing. Inheritance is a mechanism whereby an object can inherit elements from another. Wow, words are a difficulty today. Can inherit elements from another object's definition, thus gaining the parent object's data and behavior without you having to define them again. If a language must have inheritance to be an object-oriented language, then Rust is not one. There's no way to define a struct that inherits the parent struct fields and method implementations without using a macro. So the answer is you absolutely can use inheritance. It's just not a direct feature. You just have to build it yourself. However, if you're used to having inheritance in your programming toolbox, you can use other solutions in Rust, depending on your reason for reaching for inheritance in the first place. You would choose inheritance for two main reasons. One is for reuse of code. You can implement particular behavior for one type, and inheritance enables you to reuse that implementations for a different type. You can use this in a limited way in Rust, Rust code, using default trait method implementations, which you saw in listing 10.14. When we added a default implementation to the summarize method on the summary trait, any type implementing the summary trait would have the summarize method available on it without any further code. This is similar to a parent class having an implementation of a method, and an inheriting child also having the implementation of the method. We can also override the default implementation of the summarize method when we implement the summary trait, which is similar to a child class overriding the implementation of a method inherited from a parent class. The other reason to use inheritance relates to the type system, to enable a child type to be used in the same places as a parent type. This is also called polymorphism, which means that you can substitute multiple objects for each other at runtime if they share certain characteristics. Yeah, that I think would have to have some help from the developers in order to maintain. Perhaps. No, I think you still could code that without like a structure to keep that in place. To many people, polymorphism is synonymous with inheritance, but it's actually a more general concept that refers to code that can work with data of multiple types. For inheritance, those types are generally subclasses. Rust instead uses generics to abstract over different possible types, and trait bounds to impose constraints on what those types must provide. This is sometimes called bounded parametric polymorphism. Okay, I guess that's the terminology for the generics that we've been seeing and how they've been used in quite a few of these chapters. I like that term, bounded parametric polymorphism. Inheritance has recently fallen out of favor as a programming design solution in many programming languages, because it's often at risk of sharing more code than necessary. Subclasses shouldn't always share all characteristics of their parent class, but will do so with inheritance. This can make a program's design less flexible. It also introduces the possibility of calling methods on subclasses that don't make sense, or that cause errors because the methods don't apply to the subclass. In addition, some languages will only allow single inheritance, meaning a subclass can only inherit from one class, further restricting the flexibility of a program's design. These rigid structures are something I strongly disagree with. Let programmers be free. Of course, they use their freedom poorly. I will admit, I've seen some horrifically designed Java programs. For these reasons, Rust takes the different approach of using trait objects instead of inheritance. Let's look at how these trait objects enable polymorphism in Rust. You have a single quiz. Oh no! Which of the following aspects of object-oriented programming does Rust implement? Inheritance of superclass methods? They do not. Encapsulation of private data? They do. Objects with methods? In a way, sure. This might be wrong because they might count inheritance of superclass methods. I would, but I don't think they will. So let's see. I'm correct, they didn't. Rust contains objects, i.e. structs, and encapsulation via the pub keyword, but not inheritance. Unless you do it yourself. Alright. Using trait objects that allow for values of different types. In Chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing 8.9 where we defined a spreadsheet cell enum that had variants to hold integers, floats, and text. This meant we could store different types of data in each cell and still have a vector that represented a row of cells. This is a perfectly good solution when our interchangeable items are a fixed set of types that we know and when our code is compiled. However, sometimes we want a library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example graphical user interface, GUI, tool that iterates through a list of items, calling a draw method on each one to draw it on the screen. A common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image and another might add a select box. We won't implement a fully fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing this library, we can't know and define all the types other programmers might want to create, but we know that GUI needs to keep track of many values of different types, and it needs to call a draw method on each of those differently typed values. It doesn't need to know exactly what will happen when we call the draw method, just that the values will have that method available for us to call. To do this in a language with inheritance, we might define a class named component that has a different named draw on it. The other classes, such as button, image, and select box, would inherit from component, and thus inherit the draw method. They could each overwrite the draw method to define their custom behavior. but the framework could treat all of the types as if they were component instances and call draw on them. But because Rust doesn't have inheritance, we need another way to structure the GUI library to allow users to extend it with new types. Defining a trait for common behavior. Okay, I don't really have much to say right now. We've gone, oh my god, this is going to be a very long one. Heh. To implement the behavior we want GUI to have, we'll define a trait named draw that will have one method named draw. Then we can define a vector that takes a trait object. A trait object points to both an instance of a type implementing our specified trait and a table used to look up trait methods on that type at runtime. Okay, I don't think I fully understand what it's saying. I would love to see some code. We create a trait object by specifying some sort of pointer, such as a reference, or a box, smart pointer. Then the dyn keyword. And then specify the relevant trait. We'll talk about the reason trait objects must use a pointer in Chapter 19, in the section Dynamically Sized Types and the Sized Trait. We can use trait objects in place of a generic or concrete type, wherever we use trait object. Rust type system will ensure at compile time that any value used in that context will implement the trait's object trait. Oh, okay. Is this one of the major reasons why we can't have pre-compiled libraries? Consequently, we don't need to know all the possible types at compile time. We have mentioned that, in Rust, we refrain from calling structs and enums objects to distinguish them from other languages' objects. In a struct or enum, the data in the struct field and the behavior in impl blocks are separated, whereas in other languages, the data and behavior combined into one concept is often labeled an object. However, trait objects are more like objects in other languages in the sense that they combine data and behavior, but trait objects differ from traditional objects in that we can't add data to a trait object. Trait objects aren't as generally useful as objects in other languages. Their specific purpose is to allow abstraction across common behavior. Right, and here we are showing how to define a trait called draw with one method named draw. Okay, yeah. The syntax should look familiar from our discussions on how to define traits in Chapter 10. Next comes some new syntax. Listing 17.4 defines a struct named screen that holds a vector named components. This vector is of type box dyn draw, which is a trait object. It is a stand-in for any type inside a box that implements the draw trait. We have a public struct screen with a public component holding a vector which holds boxes, each holding a dyn draw. I'm guessing I'm not just forgetting what dyn is, and that dyn is a new keyword that we've just learned. Either that or I am just drawing a massive blank. On the screen struct, we'll define a method named run that will call the draw method on each of its components as shown in listing 17.5. Inside of the impl block, we have a function called run taking in itself, a reference to. For component in self.components, creating an iterator, component.draw. We're just drawing all components inside of that vector, holding boxes, holding dynamic draws. This works differently from defining a struct that uses a generic type parameter with trait bounds. A generic type parameter can only be substituted with one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the traits objects at runtime. For example, we could have defined the screen struct using a generic type and a trait bound as in listing 17.6. We have a public struct string, which simply has a public components, which is vector of any type. Implementing on screen, holding any type of any type, where the trait draw is set where it exists. A public function run, which just runs these pieces. This restricts us to a screen instance that has a list of components of all type button or all type text fields. If you'll only ever have homogeneous collections, using generics and trait bounds is preferable, because the definitions will be monomorphized at compile time to use the concrete types. A little bit. I don't exactly know what's going on. That's okay though. On the other hand, with the method using trait objects, one screen instance can hold a vector, which contains a box holding buttons, as well as a box holding text fields. Okay, yeah, I guess what it's saying here is that this can only hold one type. However, utilizing a trait object in this sense will allow us just to have multiple types. Is that really just what it's saying? Okay, fair. Yeah, I'm incredibly tired and sorry for missing that. Implementing the trait. Now we'll add some types that implement the draw trait. We'll provide the button again. We'll provide the button type. Again, actually implementing a GUI library is beyond the scope of this book, so the draw method won't have any useful implementation in its body. To imagine what the implementation might look like, a button struct would have fields for width, height, and label. Width, height, labels, right? Go to actually run the button. We have implementing draw for button. Function draw, which takes itself, which meets our definition way up. Well, it's somewhere, you know. The width, height, and label fields on button will differ from the fields on other components. For example, a text field might have those same fields plus a placeholder field. Each of those types we want to draw on the screen will implement the draw trait, but we'll use different code in the draw method to define how to draw that particular type. As button has here, without the actual geocode as mentioned, the button type, for instance, might have an additional impl block containing methods related to what happens when a user clicks the button. These kinds of method won't apply for types like text field. If someone using our library decides to implement a select box struct that has width, height, and options fields, they implement the draw trait on select box type as well. As shown in listing 17.8, use GUI draw, select box having all these pieces, and then they just implement draw the same as you would previously. Our library's user can now write their main function to create a screen instance. To the screen instance, they can add a select box and a button by putting each in a box to become a trait object. They can then call the run method on the screen instance, which will call draw on each of the components. Listing 17.9 shows this implementation. Alright, so we have let screen equal a new screen holding a components object. Where the components object is a vector. Inside of that vector, we have a new box. Inside of that box is a select box with this data. Then, separately, within the vector, which is held in the components property of screen, we implement a button, which is a box new, holding in the button. Screen.run will just go through each of these boxes, try and run the run method on it, which will go down into the select box and check for the run trait, not method, trait. When we wrote the library, we didn't know that someone might add the select box type, but our screen implementation was able to operate on the new type and draw it because select box implements the draw trait, which means it implements the draw method. The concept of being concerned only with the messages a value responds to rather than the value's concrete type is similar to the concept of duck typing in dynamically typed languages. If it walks like a duck and it quacks like a duck, then it must be a duck. In the implementation of run on screen in listing 17.5, run doesn't need to know that what the concrete type of each component is. It doesn't check whether a component is an instance of a button or a select box. It just calls the draw method on the component. By specifying box, dine, draw as a type of the values in the components vector, we've defined screen to need values that call the draw method on. Okay? The advantage of using trait objects in Rust type system to write code similar to code using duck typing is that we never have to check whether a value implements a particular method at runtime, or worry about getting errors if a value doesn't implement a method, but we call it anyway. Rust won't compile it, and will throw it back to you if you fuck up. Right? Here's what happens if we try and create a screen with a string as a component. Yeah, it's just going to error out saying that string does not implement the run method, I'm assuming. Right, the trait bound string draw is not satisfied. Okay, that's the error. The trait bound string draw is not satisfied. The trait draw is not implemented for string. Help, the trait draw is implemented for button. Oh, so it will look into like our code and just say, hey, it is implemented for button. Like there's another thing over here called button. No, required for the cast from string to the object type of dine draw. Okay. What just moved? Alright. The error lets us know that either we're passing something to screen that we didn't mean to pass, and so should pass a different type, or we should implement draw on string, so that string is able to call draw on it. Trait objects and type inference. One downside to using trait objects is how they interact with type inference. For example, consider type inference for vector of any type. When any type is not a trait object, Rust just needs to know the type of a single element in the vector to infer the type. So an empty vector causes a type inferencing error. Error E0282. Type annotation needed for a vector of any type. But adding an element enables Rust to infer the type of the vector. And we don't need to just outright tell. Type inference is trickier for trait objects. For example, say we tried to factor the components array in listing 17.9 into a separate variable, like this. You have a component, which is a vector of boxes, and that screen equal a new screen holding the components. Sorry. Right. This refactor causes the program to no longer compile. The compiler rejects this program with the following error. We have mismatched types. We have arguments to this function are incorrect. Expected select box found button. Ah, okay. Since components is simply a vector, it'll look at the first piece of the vector to infer the type. I see. And thus, since the type is just inferred as select box, once it hits button, it's going to think, hey, you messed up. Now, listing 1709, the compiler understands that the components vector must have the type box, dine, draw, because that's specified in the screen struct definition. But in listing 1711, the compiler loses that information at the point where components is defined. To fix this issue, you have to give a hint, the type inference algorithm. Huh. I don't understand why, actually, now. That can either be via an explicit cast on any element of the vector like this, as box, dine, draw. Okay. Right, so what is the issue exactly? I don't fully understand, so I'll be clear. We have a box new button. Arguments this function are correct. Expected select box found button. what exactly is wrong here? Because both of these are boxes with new pieces. But they haven't been... Okay, but they haven't been explicitly stated to be dying types? I guess it thinks the vector contains a certain type? I guess so, but it doesn't break... It doesn't break here. It breaks within some separate piece. No, 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 I'm sorry, this is just concatenated. It does break here. I'm sorry, you are correct. Yeah, I'm sorry, you are correct. I guess I was kind of correct at the first point. I just confused myself. Yeah, I guess so. So yeah, just to confirm, it does look inside of the vector, see a select box, say, hey, this is a select box vector, this is a vector type select box of type boxes holding the type select box. I see. There we go. That is what it thinks it is. It believes that it's a vector holding boxes which hold select boxes. And separately, when we get here, it messes up. However, separately, we can here cast directly to as box dine draw. Okay. Thank you for the help, Sorbet. Always here to bring me back to center. Or it can be via type annotations on the let binding like this. Let components of type vector box dine draw equal vector box new select box. In general, it is good to be aware that using trait objects can cause a worse developer experience for API clients in cases of type inference. Right. Trait objects perform dynamic dispatch. Recall in the performance of code using generic section in chapter 10, our discussion on the monomorphization process performed by the compiler when we use trait bounds on generics. The compiler generates non-generic implementations of functions and methods for each concrete type that we use in place of a generic type parameter. The code that results from monomorphization is doing static dispatch, which is when the compiler knows what methods you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time which methods you're calling. In dynamic dispatch cases, the compiler emits code that at runtime will figure out what methods to call. When we use trait objects, Rust must use dynamic dispatch. The compiler doesn't know all the types that might be used with the code that's using trait objects. So it doesn't know which method implemented on which type to call. Instead, at runtime, Rust uses the pointers inside the trait object to know which method to call. This lookup incurs a runtime cost that doesn't occur with static dispatch. Dynamic dispatch also prevents the compiler from choosing to inline a method's code, which in turn prevents some optimizations. However, we did get extra flexibility in the code that we wrote in listing 17.5, and we're able to support in listing 17.9, so it's a trade-off to consider. This is the most common trade-off in programming. Do you want easy code to write, understand, and expand upon, or do you want code that's performant? For the past 6-7 years, it looks like, more than that, honestly, maybe 10-15 years even, the trade-off has almost always gone towards the idea of better developer experience, quicker iteration, better expansion of the current code base. However, the reason I guess why a lot of people would be quite against utilizing it in Rust is because Rust is the revolution on going back to as performant code as humanly possible. Giving up that optimization for something like OOP just doesn't seem valuable to a lot of people, I can imagine. Determine whether the program will pass the compiler. If it passes, write the expected output as if it were executed. Right, we have n equals 1, s equals string from hello. We have a v, which is a vector, holding a reference to a dynamic debug, which equals a vector of references to n and references to s. Sorry. Yeah, that's correct. Reference to 1 and reference to a string from hello. I'm unsure. I don't think this will compile. Let nref equal the first element in the vector v as a reference to an I32. That would be what you'd have to do. You'd have to cast it back to an I32 instead of a dynamic debug, a standard format debug. Alright, and then we print nref plus 1. Now I'm unsure. This will be where I really get to understand what... I don't know what I was going for there. I really don't know, so I'm just going to say it doesn't compile. My issue here is that this is not a box. The vector does not hold a singular type. It holds both a string and a type 1. It does not explicitly state or cast to a dynamic reference to a debug. So I believe this is going to be an issue here, because a vector should only be able to hold one singular type of object. I wouldn't be surprised if I'm wrong here, however. But this is what I'm going to say, that it does not compile. Right, consider implementing a generic function in two ways. We have a function, fnopt1, which returns any type with some trait, taking in t, which is a reference to something with the same type. Option 2 takes in the type with a dynamic some trait reference. In most cases, which of the following are good reasons to refer the trait object version fopt2 over the type parametric version? God. Type parametric version fopt1. Select each that applies. Right, so it's been stating better development ergonomics. It is not a smaller binary size. In fact, I think it might be a little bit larger because of that check. Improved runtime and performance is incorrect. In fact, it'll do the opposite. And faster compile times. I don't know, actually. It hasn't stated that explicitly, but I wouldn't be surprised if it does, because it doesn't have to compile all of the checks. It doesn't have to run all of those checks until runtime. If it was running those checks at runtime, it would, of course, compile faster, I'd assume. But it didn't explicitly state that, so I think I'm going to go without it. I think the only real reason is better developer ergonomics. I only got one correct. It does not compile. But I'm guessing that better compile times is something that was here. Yeah, faster compile times is correct. Let's read this one first, just to clarify. Unlike some OOP languages, a trait object cannot be downcasted to a more concrete type, except in cases of the any trait. Okay. Secondarily, by avoiding monomorphism, a trait object function will be both faster to compile and produce smaller binaries. Oh, it's not actually better to... Okay. Faster to compile and produce smaller binaries. However, this usually comes at a cost of runtime performance. Trait objects are rarely easier for developers to work with than trait-bounded generics. Okay. This seems more familiar. I'm sorry, from everything that I've read, this seems more familiar from a guy coming from object-oriented like. But I can just... No, I really can't, actually. I guess I'd have to work with both, but, hey. So the correct answer is that faster compile times and smaller binary sizes are the particular reason why a person would use the trait object version instead of the type parametric version. Okay, these things are not good reasons. I'm sorry. Faster compile times are meaningless. Smaller binary size is meaningful, actually. That's fair. Alright. Implementing an object-oriented design pattern. A state pattern is an object-oriented design pattern. The crux of the pattern is that we define a set of states a value can have internally. The states are represented by a set of state objects, and the value's behavior changes based on its state. We're going to work through an example of a blog post struct that has a field to hold its state, which will be a state object from the set draft, review, or publish. The state objects share functionality. In Rust, of course, we use structs and traits rather than objects and inheritance. Each state object is responsible for its own behavior and for governing when it should change to another state. The value that holds a state object knows nothing about the different behaviors of the states or when to transition between states. The advantages of using the state pattern is that when the business requirements of a program changes, we won't need to change the code of the value holding the state or the code that changes the value. We only need to update the code inside one of the state objects to change its rules, or perhaps add more state objects. We're going to implement the state pattern First, we are going to implement the state pattern in a more traditional object-oriented way. Then we'll use an approach that's a bit more natural in Rust. Let's dig into incrementally implementing a blog post workflow using the state pattern. The final functionality will look like this. A blog post starts as an empty draft. When the draft is done, a review of the post is requested. When the post is approved, it gets published. Only published blog posts return content to print, so unapproved posts can't accidentally be published. Any other changes attempted on a post should have no effect. For example, if we try to approve a draft blog post before we've requested a review, the post should remain an unpublished draft. Listing 1711 shows this workflow in code form. This is an example usage of the API we'll implement in a library crate named blog. This won't compile yet because we haven't implemented the blog crate. Use blog post. Alright, so we got function main is immutable post, post new. Post.add text, I eat salad, yep. Assert equal that the post contents equal nothing. So if we create a post and then try and add the text, we need to know that there's nothing within the contents. If we request a view, there's nothing within the contents. However, once it is approved, I ate salad for lunch today is output. So it does store the value. However, it will not actually output the value until it is approved. We want to allow the user to create a new draft blog post with the post new. We want them to, by the way, test-driven development here. Just a little bit of that. We want to allow the user to create a new draft blog post with the post new. We want to allow text to be added to the blog post. If we try to get the post content immediately before approval, we shouldn't get any text because the post is still a draft. We've added assert equal in the code for demonstration purposes. An excellent unit test for this would be to assert that a draft blog post returns an empty string from the content method. But we're not going to write tests for this example. Next, we want to enable a request for a review of the post, and we want content to return an empty string while waiting for the review. When the post receives approval, it should get published, meaning the text of the post will be returned when content is called. Notice that the only type we're interacting with from the new crate is the post type. This type will use the state pattern and will hold a value that will be one of 3 state objects representing the various states a post can be in: draft, waiting for review, or publish. Changing from one state to another will be managed internally within the post type. The state change is in response. The states change in response to the method called by a library's user on the post instance, but they don't have to manage the state directly. State changes directly. God, I cannot speak today. Whatever. Also, users can't make a mistake with the states, like publishing a post before it's reviewed. How do you get content for a review? Defining post and creating a new instance in the draft state. Let's get started on the implementation of the library. We know we need a public post struct that holds some content, so we'll start with the definition of the struct and an associated public new function to create an instance of post. As shown in listing 1712, we'll also make a private state trait that will define the behavior of all state objects for a post must have. What? Sorry, that's terribly written. That's not me. We'll also make a private state trait that will define the behavior that all state objects for a post must have. Never mind, I am an idiot. That is perfectly well written. Then posts will hold a trait object for box dying state inside an option in a private field named state to hold the state object. You'll see why the option T is necessary in a bit. Right, inside of file name source lib.rs, I'm guessing we were supposed to write this all? I'm not going to do that right now though. Public struct post state, which is an option, holding a box, holding a dynamic state object. Content is just a string. We're implementing on post a new function called new, which returns a post. The post has an empty state, which holds a sum object, which holds a box, which holds a new box holding a draft, which is empty. That is the state. Right, content is just a new string. We have a trait, state, and a struct, draft. Implementing state for draft is nothing. Okay. Definition of a post struct and a new function that creates a new post instance, a state trait, and a draft struct. The state trait defines the behavior shared by different post states. The state objects are draft, pending review, and published, and they will all implement the state trait. For now, the trait doesn't have any methods, and we'll start by defining just the draft state, because that is the state we want new posts to start in. When we create a new post, we set its state field to a sub value that holds a box. This box points to a new instance of the draft struct. This ensures whenever we create a new instance of a post, it will start out as a draft. Because the state field of a post is private, there's no way to create a post in any other state. In the post new function, we set the content field to a new empty string. Alright. Storing the text of a post's content. We saw in listing 1711 that we want to be able to call a method named addText and pass it a string slice. That is then added to the text content of the blog post as a method, rather than exposing the content field as pub. So that later we can implement a method that will control how the contents field data is read. The addText method is pretty straightforward, so let's add the implementation listing 1713 to the impl post block. Alright, so you have an implement block on. Sorry about that. Accidentally moved my drawing tablet and it decided to start moving. I didn't think that was plugged in. Right, so implementing on post a public function addText, which takes in a mutable reference to self, and text, which is a string reference. Self.content.pushString text just pushes text to the string. To content. The addText method takes a mutable reference to self, because we're changing the post instance that we're calling addText on. Yep. We then call pushString on the string in content and pass the text argument to add to the saved content. This behavior doesn't depend on the state the post is in, so it's not part of the state pattern. The addText method doesn't interact with the state field at all, but it is part of the behavior we want to support. Okay. Ensuring the content of a draft post is empty. After we've called addText and added some content to our post, we still want the content method to return an empty string slice because the post is still in the draft state. as shown in line 7 of listing 1711. For now, let's implement the content method with the simplest thing that will fulfill this requirement. Again, test-driven development. Always return an empty string slice. We'll change this behavior later once we implement the ability to change a post state, so it can be published. So far, posts can only be in the draft state. So, post content should always be empty. Listing 1714 shows the placeholder implementation. Right, so implementing on post, public function content, which takes a reference to itself, and returns a string slice, and here we go. I hate this so much. You're never going to get me to stop saying this. That is so dumb. Anybody who doesn't know how this trash works would not have a clue what's going on here. It's just returning an empty string, but it infuriates me that I can't just put the word return here because that's not idiomatic Rust. Alright though. With this added content method, everything in listing 1711 up to line 7 works as intended. Requesting a review of the post changes its state. Next, we need to add functionality to request a review of a post, which should change its state from draft to pending review. Listing 1715 shows this code. Right, so we got a public function, request review, taking an immutable reference to self, implemented on post, if let, sum s, letting s equal self.state.take. Alright, if that outputs a sum, dot take. I don't think I've ever seen that method. Who cares? I assume that just... I actually don't know what that does. Self.state.equals sum s.request review. Okay, yep. So that'll equal an option s.request review, whatever the output is here. I'm sorry, what? Yeah, okay, yeah. So this is implemented on state. Right, so implement state for draft. Function request review. Right, so implementing on the state trait for draft, we are adding in the function, so we're implementing the function request review on the state trait for draft, the struct. And here's the code for it. We have on the post block, on the post struct, we are implementing the function request review of the same name we will see in state for draft. And inside of it, we will run the s.requestReview, s being the state from the main object of draft, from the main object of post, which will be part of draft at this point. But it could be a draft in review or a published, I believe. We'll see that later. But currently, this will always be from draft. Okay, so this is how okay, so this is how it implements the same function on every piece. Okay, this kind of makes sense now. Okay, so I think I understand what's going on. So self.state.take will take the post.state's value, which can be a draft, but can also be two other structs, or many other structs. So this will take one of any of these structs, draft, in review, or publish, and if it exists, it will output the sum object with the state, which is another object. Not really. It'll be draft, in review, or published. And then from that, stuff.state will equal sum, an option. It'll have that value. If it got to here, it has to have that value. And run s.request review. which I'm guessing here. Here, if we look at the implementation of request review for draft, it takes in a self, box self, outputs a box dynamic state, and then the box new pending review here. So this will change the state inside of request review. But it doesn't know that. This function here does not know that it's changing state. It never needs to know that it's changing state. It doesn't actually need to change state. Requesting a review does change state, but if there's some weird thing here that doesn't change state, it doesn't need to. Self.state is being changed here no matter what, of course, but it doesn't need to go away from draft is what I'm saying. It'll just be a box no matter what, but it can be any different type of box, I believe. I'm sorry, I've been rambling here for a bit. I'm guessing that it will... Yeah, so I'm guessing that it will eventually discuss what's going on here. So I'm just going to continue forward, right? So we also have the struct in pending review, which implements state for pending review. Function, request review. Allow in section. Yeah, I will admit I did not think that was there. Secret second section. Implement state for pending review, which just outputs self. So if you call pending review on something that's already a pending review, it just gives back the self state, which will change the state back to itself. It won't actually change the state, but I mean, it kind of will. It'll change the state back to itself. Okay. I think I fully understand what's going on here, but I would fully understand if a person didn't. I'm guessing they're going to describe it a hell of a lot better than I do. Right. We give post a public method called request review that will take a mutable reference to self. Then we call an internal request review method on the current state of post. And the second request review method consumes the current state and returns a new state. We add the request review method to the state trait. All types that implement the trait will now need to implement the request review method. Note that rather than having self, reference to self, or a mutable reference to self as the first parameter of a method, we have self, a box holding self. I did see that. I didn't fully know. This syntax means the method is only valid when called on a box holding the type. Okay? The syntax takes ownership of box self, invalidating the old state, so the state value of the post can transform into a new state, which sometimes will be the same state. Transform into a new state, exactly what you were before. To consume the old state, the request review method needs to take ownership of the state value. This is where the option in the state field of post comes in. We call the take method to take the sum value out of the state field and leave a none in its place, because Rust doesn't let us have unpopulated fields in structs. This lets us move the state value out of post rather than borrowing it. Then we'll set the post state value to the result of this operation. This is elegant but incredibly hacky. Alright. Where was I? Yep. We need to set the state to none temporarily, rather than setting it directly with code like self-state equals self-state request review to get ownership of the state value. This ensures post can't use the old state value after we've transformed it into a new value. Good. Will it? I'm guessing it'll complain and then fail if you try it without that. No, it actually probably wouldn't now that I think about it, since it is just... Okay. The request review method on draft returns a new boxed instance of a new pending review struct, which represents the state when a post is waiting for a review. The pending review struct also implements the request review method, but doesn't do any transformations. Rather, it returns itself, Because when we request a review on a post already in pending review state, it should stay in the pending review state. Now we can start seeing the advantages of the state pattern. The request review method on post is the same no matter what its state is, no matter what value is inside state. Each state is responsible for its own rules. We'll leave the content method on post as is, returning an empty string slice. We can now have a post in the pending review state as well as in the draft state. Well, we want the same behavior in the pending review state. Listing 1711 now works up to line 10. I will admit, TDD breaks my brain. I really, really hate, well, I don't know why I'm scrolling down. I really, really hate not implementing that piece on the content method. I put in some boilerplate code to have it work one way or the other, and then start implementing the trace myself. But that's not really TDD. That's not what they want me to do. It's something that just, I don't know, just not how I think personally. The approve method will be similar to the request review method. It will set state to the value that the current state says it should have when the state is approved, as shown in listing 1716. We are implementing on post the public function approve, taking an immutable reference to self. If let sum s equals state self.state.take. Okay, yeah, so sorry to just recenter. Self.state.take takes state, takes ownership over state, turning it from a sum value into a none value, returning a sum value as s. Sorry, returning a sum value with the original piece in it, which is then utilized in the if let sum, taking the value of s here, also ensuring that if it is none, this fails. If it doesn't fail, self.state equals sumState.approve. That is the same as we have seen in the previous section. Right? Same essential code, just different naming, really. Right, so then we have a trait with state in it, which has request review and approve, which needs to hold a self, which needs to take in a self, which is a box with self in it. Returning a box dynamic state. A boxed dynamic state. We have a struct draft, still as it was before, implementing state for draft, function approve. We have the previous code there too. Taking in self, it just... What? Right, so if you try and approve draft... okay, yeah. If you try and approve draft, nothing happens, and it just returns its current state, which is draft. So if you try and approve a draft, it'll just still stay a draft. It will do no work. Of course, I should state with all of this code that you should inform the user of your library that it isn't changing something from a draft to a published here. And inside of here, we have struct pending review, implementing approve. And if it works, it simply outputs a new box holding a published, what is the word? What is the word? A struct. Gosh, a published struct. There we go. Huh. So implementing state for published. We have a new struct here called published. Implementing state for published. Function request review, just return self. And approve, just return self. Because published must implement request review and approve, as it must implement state in order to be utilized in the same method. We must just implement it and return self. Honestly, I really like this method. It's a bit more code than you might need in some languages, but like in another language with inheritance that's just built in without. Of course, you could use a macro for this, but unlike other languages with inheritance, we would have like a state object which approve, request review, and approve would just return self by default. And each of these, pending review and draft, would just overwrite request review or approve each on themselves. Here, we have to repeat code constantly. If we have 14 different functions here, each of these, publish, draft, state, would have to have 14 different functions on it, each of them doing essentially nothing because they're not useful, which is a bit of a shame. That can make things unmaintainable and difficult to read. Of course, with macros, we don't need that. When are we learning about macros? Are we learning about macros? Yeah, we're learning about macros soon enough. Good stuff. I don't know if that's an advanced feature, honestly. We add the approve method to the state trait and add a new struct that implements state and publish state. Implement state. We add the approve method to the state trait and add a new struct that implements state, the published state. We add the published state, which implements state. Similar to the way request review and pending review works. If we call on pending review works, if we call the approve method on a draft, it will have no effect because approve will return self. When we call approve on pending review, it returns a new boxed instance of the published struct. The published struct implements the state trait, and for both the request review method and the approve method, it returns itself. Because the post should stay in the published state in those cases. Now we need to update the content method on post. We want the value returned from content to depend on the current state of the post. So we're going to have the post delegate to a content method defined on its state, as shown in listing 1717. Right? So we have a public function content taking in a reference to self and outputting string self.state.asref.implement.content self. Wow. Okay. Okay, yeah. Right. So we're getting state as a reference and then unwrapping it so that it's no longer inside of an option. And then we're calling the content method, passing in the self reference we have here. Right, sure. Because the goal is to keep all these rules inside the struct that implements state, we call a content method on the value in state and pass the post instance, that is self, as an argument. So again, here, we're going to have to implement content on every single different struct that we have so far. When we return the value that's returned, then we return the value that's returned from using the content method on the state value. Yeah, but we don't tell you that, though. You gotta look here to see that there's no semicolon. We call the asref method on the option because we want a reference to the value inside the option rather than ownership of the value. Because state is an option box dynamic state. When we call asref, an option reference box dynamic state is returned. If we didn't call asref, we would get an error because we can't move state out of the borrowed reference self of the function parameter. Of course not. So we need to borrow it ourselves. We then call the unwrap method, which we know will never panic, because we know the methods on post ensure that state will always contain a sum value when those methods are done. Will always contain a sum value when those methods are done. However, what we have introduced into our code is the ability for somebody else not to understand that and cause it to at one point have a none value, particularly with the fact that we put a none value in state during the code's operation. And thus, we have in our code a pathway to a failure, to a panic, and this should be documented. This isn't a bad thing, but this definitely should be documented. Any call to unwrap should be put in a place There should be some reference in whatever documentation you're building while you're writing the code that states that this function can panic, and that this object that you're creating has panicable code inside of it. You never want your code to die in operation. This is one of the cases we talked about in the cases in which you have more information than the compiler section of Chapter 9, when we know that a none value is never possible, even though the compiler isn't able to understand that. Okay? At this point, when we call content on the reference box dynamic state, deref coercion will take effect on the reference and the box, so the content method will ultimately be called on the type that implements the state trait. This means we need to add content to the state trait definition, and that is where we'll put the logic for what content to return depending on which state we have, as shown in listing 1718. Right? So we have public trait. So we have on the trait state a function called content with lifetime of a. Yep. A reference to self, taking in a reference to self, and a post, which is a reference with a lifetime of a, of type post, returning a reference with the same lifetime as what is passed in to a string. Then we just return nothing, of course. And in the struct publish, we implement state for published inside of a function, content, with a lifetime of a, taking in a reference to self and a post, of a post object with the same lifetime, and returning with the same lifetime a reference to a string, or a string slice. Then we just return a reference to the post.content, which is whatever we put in when we created it, or when we ran draft. When we created it. Whatever it was, I don't care. We add a default implementation for the content method that returns an empty string slice, which is good. I'm glad that we have this default here. That's good to just bash into you that this is the default behavior, that it just has that. Wait, why not? Because never mind, I'm an idiot. Whatever it is. But wait, no, because the new piece. Never mind, it makes sense, because new does add it in, but we can't actually get the content until it is published. Why just get the content originally? The default should be just nothing. That's fine. That actually lowers the amount of code that we have to have. I'm sorry, actually, that makes sense. Here is essentially overloading. Okay, never mind. I'm sorry, that does make a lot more sense than I thought it originally did. That means we don't need to implement content on the draft and pending review structs because we have a default. The publish struct will override the content method and return the value in post.content. Okay, that's a bit embarrassing. I was complaining about something that is not a problem because we have a default implementation. Which we could have done with the returning self. That could have been the default too for everything else as well. At which point we'd only have to implement what we needed to overload. So let's just go up here. We wouldn't actually need to implement improve if we just had a default in state that returns self. Same with the other one, request review. If we just had a default that returns self. No. Never mind, because it needs to return a box dynamic state. No, never mind. Yeah. This is just a default. We could have done that, I think. I don't see what the problem would be. Okay. Yep. Note that we need lifetime annotations on this method because we don't know how long what was passed in the post object has. So we need, as we discussed in chapter 10, we're taking a reference to a post as an argument and returning a reference to part of that post. So the lifetime of the returned reference is related to the lifetime of the post argument. And we're done. All of listing 11.17 now works. We've implemented the state pattern with the rules of the blog post workflow. Logic related to the rules lives in the state objects rather than being scattered throughout post. Why not an enumeration? Why not an enum? You may have been wondering why we didn't use an enum, with the different possible post states as variants. That's certainly a possible solution. Try it and compare the end results to see which you prefer. One disadvantage of using an enum is that every place that checks the value of the enum will need a match expression or similar to handle every possible variant. Yeah, we couldn't just implement on the struct. This would get more repetitive than this trait object solution. Make sense? Would it be quicker or slower? No, it would be slower, of course, I think. What would the value be in that? Trade-offs of the state pattern. We've shown that Rust is capable of implementing the object-oriented state pattern to encapsulate the different kinds of behavior a post should have in each state. The methods on post know nothing about the various behaviors. The way we organize the code, we have to look in only one place to know the different ways. That's what you're asking the entire time? Fair. I really think that this is just showing us different ways in which it can be done. I don't think it actually wants us to do this at all. I don't think it wants object-oriented at all, to be honest. The way we organize this code, we have to look in only one place to know the different ways a published post can behave, the implementation of the state trait on the published struct. If we were to create an alternative implementation that didn't use the state pattern, we might instead use match expressions in the methods on post, or even in the main code that checks the state. Also, you read the next section, is a bit clearer for you. The next chapter? Inventory. Or are you talking about patterns and matching? If we were to create an alternative implementation that didn't use state patterns, we might instead use match expressions. No, like this chapter? Oh, okay. The new code. Oh, down here. Ah, I see. Getting to that closely. Wow, reading ahead. Am I that slow? Alright, that check the state of the post and changes behavior in those places. That would mean we would have to look in several places to understand all the implications of a post being in this published state. This would only increase the more states we added. Each of those match expressions would need another arm. With the state pattern, the post methods and the places we use post don't need match expressions, and to add a new state, we would only need to add a new struct and implement the trait methods on that one struct. The implementation using the state pattern is easy to extend to add more functionality. To see the simplicity of maintaining code that uses the state pattern, try a few of these suggestions. Add a reject method that changes the post state from pending review back to draft. That would be pretty easily done. That would just be implement public function reject, which would return a new box of a dynamic draft instead of itself or whatever on top of the pending review. We then have to put return self on draft or return self on the approved object. I don't know what you would do on the approved object. Or sorry, the approved state. Requiring two calls to approve before the state can be changed to publish. Yeah, we would just change the approved method to... We would just change post to hold the amount of approvals, and then secondarily, we would just increment that counter and check if it's 2 before actually returning a box of a dynamic approved. Otherwise, doing the same with draft. We would then also have to, on reject, decrement the counter, or that would just always go back to draft. Allow users to add text content only when a post is in the draft state. Hint: have the state object responsible for what might change about the content, but not responsible for modifying the post. To add text content only when it's in the draft state. Hint: have the state object responsible for what might change about this content, but not responsible for modifying the post. Okay, yeah, fair. Sure, whatever. One downside of the state pattern is that, because the state implements the transitions between states, some of the states are coupled to each other. If we add another state between pending and published, such as a schedule, we would have to change the code in pending review to transition to scheduled instead. It would be less work if pending review didn't need to change with the addition of a new state, but that would mean switching to another design pattern. But not the enumeration pattern. The enums pattern wouldn't work in that either. You'd still have to change a lot of code to do that. Another downside is that we've duplicated some logic. To eliminate some of the duplication, we might try to make default implementations for the request, review, and reprove methods on the state trait that return self. I agree. However, this would violate object safety because the trait doesn't know what the concrete self will be exactly. That's true. That's fair. Actually, yeah, that's fair. We want to be able to use state as a trait object, so we need its methods to be object safe. That is understandable. Other duplication includes a similar implementation of the request, review, and approve methods on post. Both methods delegate to the implementation of the same method on the value in the state field of option. What? Delegate. And set the new value of the state field to the result. If we had a lot of methods on post that followed this pattern, we might consider defining a macro to eliminate the repetition. See macros in chapter 19. By implementing the state pattern exactly as it's defined for object-oriented languages, we're not taking as full advantage of Rust's strengths as we could. Let's look at some changes we can make to the block trait that can make invalid states and transitions into compile time errors. That is really cool. That is really cool. I like that. Encoding states and behaviors as types. We'll show you how to rethink the state pattern to get a different set of trade-offs, rather than encapsulating the states and transitions completely so outside code has no knowledge of them. We'll encode the states into different types. Consequently, Rust's type checking system will prevent attempts to use draft posts, where only published posts are allowed by issuing a compiler error. Okay. We have a function, let mutable post equal post new. Post that adds text, hey, add I ate a salad. Secondarily, we try and post.content, and we no longer have to warn the person. As I was stating previously, you should warn them that this can't be used, and that warn is to just break their compiler and say, hey, you fucked up. We still enable the creation of new posts in the draft state using post new, and the ability to add text in the post content. But instead of having a content method on a draft post that it returns an empty string, we'll make it so draft posts don't have the content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us that the method doesn't exist. As a result, it'll be impossible for us to accidentally display draft post content in production, because that code won't even compile. Listing 1719 shows the definition of a post struct and a draft post struct, as well as methods on each. This is so cool. I'm sorry, this is so cool. I mean, I wouldn't create in a new Rust program like an object-oriented paradigm. Like, why not use something else for that? There's so many more better made languages for that. But transferring over a program, well, perhaps I still use another language, but in Rust, transferring over a program, just rewriting a program from, let's say C++ or like C# or something, into Rust for its performance issues, allows us to stop all of this random trash with object issues. Like, there's so many different errors that I've seen through my lifetime of programming through object-oriented programming that this would just fix, because it tells you that you're an idiot. I am a massive idiot. I'm glad the compiler is able to tell me so very quickly. Right. Public struct post content string. Public struct draft post content string. Implementing post public function new, returning a draft post. Right, yep. Implementing on post a new public function, returning a draft post, which is a struct containing the content string. Draft post, it just creates a draft post with the content of a string new. Alright, so a public function content reference to self equals a outputs a reference string with self.content. Reference self content. Okay, I'll admit, I don't know what's going on here. Right, implementing on draft post, function add text, reference mutable self, and text, which is a string. Content.push string text. Okay, so implementing on post, which is a type in and of itself, holding content, we create a new draft post with the content. Right, why does this have to have content string? This doesn't need it. At any point in here are we using it? No, I guess it is. Public function content self outputting a string content. So yeah, content does exist on a post object, but not on a draft post, which is here. So I guess, when would you ever have a post? I doubt you would. Okay, I think I do understand what's going on here, yeah. So if you create a new post, your output with a draft post instead of a post. Inside of the draft post, it has the content, and implemented on draft post is add text, but not content. You can't actually get the content, it doesn't exist. But on post it is. I don't know how a post would be created though. Well, I guess you could just manually create one, but you know. Both the post and draft post structs have a private content field that stores the blog post's text. No, you can't actually create one normally because it's not public. The structs no longer have the state field because we're moving the encoding of the state to the types of the struct. The post struct will represent a published post, and it has a content method that returns the content. Okay, so I guess that'll just be the published post. Makes sense. Post will be created when it's approved. We just don't have that code yet, I guess. Fair enough. We still have a post new function, but instead of returning an instance of post, it returns an instance of draft post because content is private and there aren't any functions that return post. It's not possible to create an instance of post right now. That just says that right there. The draft post struct has an add text method, so we can add text to content as before. But note that draft post does not have a content method defined. So now the program ensures all posts start with a draft post, and draft posts don't have their content available for display. Any attempt to get around these constraints will result in a compiler error. Good. Implementing transitions as transformations into different types. So how do we get a published post? We want to enforce the rule that a draft post has to be reviewed and approved before it can be published. A post in the pending review state should still not display any content. Let's implement these constraints by adding another struct, pending review post, defining the request review method on draft post to return a pending review post, and defining an approve method on pending review post to return a post, as shown in listing 1720. All right. Alright, so we have a public function request review returning a pending review post, which is defined down here. We have pending review post, which just has the content from self.content, which has been pulled over from post. Alright, and inside of this, we just have the content, and on pending review post, we have the approve method, which simply returns a post holding the same content. So continually, we are passing content through and through and through, again and again and again. I hope this isn't copying and it's just like changing a reference, because that would have a lot of memory reads and writes. I assume that the compiler can be pretty smart about this, however. This is a pretty simple way of doing things, so if it can be smart, I don't see any performance penalty. But yeah, that does make sense. You are correct. And I do like this method, honestly, of just straight out changing the type itself. Instead of having state being held inside of some publish struct that then routes itself around in a fury. For every single piece, we have a different type itself, with all the methods to change type inside of it. This seems to be how a lot of other things are implemented, like the RC, or sorry, the whatever, like the previous thing about like boxes within boxes and stuff like that. That tends to be what it is, because it says, hey, if you try box new, it doesn't actually return a box, it returns this, or something like that. Boxes do return a box, but I think I understand what you mean. Alright, so you would take in post, because that's the end point you're trying to get, but post doesn't return post, which is a bit counterintuitive, but makes sense in the structure it's currently trying to show us. I like this method, honestly. I've never seen something like it before, to be clear, but I like it. The request review and approve methods take ownership of self, thus consuming the draft post and pending review post instances and transforming them into a pending review post and a published post, respectively. This way, we won't have any lingering draft post instances after we've called request review on them, and so forth. Right, so it does consume these things, and thus they were in memory and now are not. They will be deleted. Alright, so this may have some performance overhead. The pending review post struct doesn't have a content method defined on it. Well, because it's not a trade object, it no longer has a lot of the overhead that it was describing previously. Maybe the overhead here is lower. It would make sense because it doesn't have to actually check any rules. Right, the pending review post struct doesn't have a content method defined on it, so attempting to resist content results in a compiler error. As with draft post, because the only way to get a published post instance that does have a content method defined is to call the approve method on a pending review post. And the only way to get a pending review post is to call the request review method on a draft post. And there's no real duplication of code either. Well, there's a little bit, but not enough to care. Alright, pending review post is to call the request review method on a draft post. What? And the only way to get okay, sorry, read that incorrectly. But we also have to make some small changes to main. The request review and approve methods return new instances rather than modifying the struct they're called on. So we need to add more let post equal shadowing assignments. Save the returned instances. We also can't have the assertions about the draft and pending review post contents being empty strings. We also can't have the assertions about the draft and pending review post contents being empty strings. Nor do we need them. We can't compile code that tries to use the content of the post in those states any longer. The updated code in main is shown in listing 1721. Right. Let mutable post new, post.add text, hey. Let post equal post.request review, and let post equal post.approve. Alright, and this really helps with an immutable. Because immutable by default is something that Rust tries to really push forward. Even though the mutable post is post new, the new shadowed post is not mutable. Most of this isn't mutable because it doesn't need to be. The only point which we need mutation is when we try add text. That's it. That's the only point where we need mutation. So why allow post to be mutable after we've mutated for the first and only time we will ever do so? Or, well, for the section we will only do so. So it allows it to stay immutable throughout its entire behavior, which is good. And then, of course, here we have post.content, which will work. However, I will say, one of the trade-offs is that with this method, we could absolutely try post.content and have it break. It could crash the program. No, it would only do so during compile time. I'm sorry. Yeah, it would only ever do so during compile time, which is great. Okay, yeah. I'm sorry, there's no negative I can see to this, unless there's some performance offset. The changes we needed to make to main to reassign post mean that this implementation doesn't quite follow the object-oriented state pattern anymore. Transformations between the state are no longer encapsulated entirely within the post implementation. However, our gain is that invalid states are now impossible because of the type system and the type checking that happens at compile time. This ensures that certain bugs, such as display of the contents of an unpublished post, will be discovered before they make it to production, because they can't even make it to development. They can't even compile. You can't even test them. Try the task suggested at the start of this section of the blog crate, as it is after listing 1721, to see what you think about the design of this version of the code. Note that some of the tasks might be completed already in this design. Ha! Yeah, I like this design a lot. We've seen that even though Rust is capable of implementing object-oriented design patterns, other patterns, such as encoding state into the type system, are also available in Rust. You know somebody edited this from, are also available and objectively better in Rust. Don't use that trash, you absolute moron. These patterns have different trade-offs. Like what? What is the negative? Can you tell me the negatives of the thing that you just suggested? Although you might be very familiar with object-oriented patterns, rethinking the problem to take advantage of Rust features can provide benefits, such as preventing some bugs at compile time. Object-oriented patterns won't always be the best solution in Rust due to certain features, like ownership, that object-oriented languages don't tend to have. I mean, ownership absolutely can be implemented and is implemented in some object-oriented languages. And again, by some definitions, as has been stated, Rust is object-oriented. Right, summary. No matter whether or not you think Rust is an object-oriented language after reading this chapter, I disagree with the idea of an object-oriented language. Object orientation is a paradigm which can be followed or not in basically any language. You now know that you can use trait objects to get some object-oriented features in Rust. Dynamic dispatch can give your code some flexibility in exchange for a bit of runtime performance. You can use this flexibility to implement object-oriented patterns that can help your code's maintainability. Rust also has other features, like ownership, that object-oriented languages do not have. An object-oriented pattern won't always be the best way to take advantage of Rust's strengths, but is an available option. From reading this, it sounds like they don't think Rust is object-oriented. Just the way they say it. Which is fair. Next, we'll look at patterns, which are another of Rust's features that enable lots of flexibility. We've looked at them briefly throughout the book, but haven't seen their full capability yet. Let's go! I thought it was ownership inventory. Next, I guess that'll be built into it. Alright, here is the quiz. In the running example from this section, a blog post could have one of three states: draft, pending, draft, and published. In the example, each state was represented as a struct, and state patterns and state transitions the word is were, represented as trait methods returning trait objects. An alternative implementation could represent the states as an enum, like this. Right, we got an enum, blog, draft, pending review, published, and then we have here a match statement matching on those and then returning what is needed. Which of the following are good reasons to prefer the struct/trait representation over the enum representation? The use of match is slower at runtime than dynamic dispatch. I don't think so. An API client could add a new state to the system, correct? Well, I mean, you could add a new state here, it would just be difficult. Adding a new state does not require modifying methods. Is this trying to say that I guess that's not really an advantage over the enum representation because you can add a new state. Sure. Adding a new state does not require modifying methods on every other state. Correct. An API client could add a new method for all states in the system. Okay, by API client, it's talking about the struct trait representation. I mean, you could do it here, but it would be easier to do in the struct trait representation with default. Yeah, so I'm guessing it's this, honestly. Yeah, sure, let's just go with this. I got that wrong. Alright, An API could add new state into the system. That is the correct one. And adding a new state does not require modifying methods on every other state. So that one is correct. However, an API client could add a new method for all states in the system. It can, though. Okay, let's read this. Okay, this is the longest explanation we've ever had. Good to see. The struct trait approach is extensible in the sense that an API client could potentially create a new state, such as retractant, without changing the core API functionality. When adding the state, the methods for other states do not need to be changed. Whereas with enums, a client cannot add a new branch to the enum. Moreover, all match patterns must be updated when a state is added. A match is not likely to be slower than dynamic dispatch. A match is a simple branch based on an enums tag, while dynamic dispatch requires a layer of indirection through a trace object's virtual table with a non-inlined function call. An API client cannot add a new method for existing states in the struct trait approach. It can only add new states. Why not? The methods are fixed by the API author's trait That's what I was thinking. Like, you can just add a new trait definition. Note that you could add a new method which only builds on existing methods via extension traits as such. Okay, so what they were talking about here, but they didn't tell us, is for the consumer of a library. Can you add a new state? No. No, of course you can add a new state, but you can't add a new function to all different states. A new method to all different states. Unless you're writing the library, which it didn't at all state here, which annoys me. Come on. Come on. I'm sorry. That did annoy me. Right. Note that you could add a new method which only builds on existing methods via extension traits such as trait, state X, function, request review twice, self, taking in a self box, returning a box dynamic state is a trait, and then implement on something that implement, anything which implements state extension for S, function, request review twice, just returns a self.requestReview, requesting it twice. But these extensions cannot read the private data of the states. Correct. Okay, sure. Right. Honestly, we're pretty close to the end. I don't think that we can do a 6-question quiz next time, but we are going to see how far we can get through this and if we remember how ownership works. And by that, I mean me. I'm going to get owned by this ownership quiz next time. And I'm honestly not okay with that. But hey, what am I going to do? Reread the entire book before next time? I don't know. Might do. Anyway, it's been great having you, Sorbet. Thank you for helping me out in a few situations. Incredibly tired today, and things are just falling straight out my head. Always good to have you, but this is goodbye for tonight. I'll see you next week. But this will be it. Once more, thanks for having me.